So when we left off, we were staring at this little chart and the chart after it and trying to make sense out of it. So we just revisit this for a few seconds before we move on. So the point we're trying to drive home here is that when we start talking about dB SPL, or dB sound pressure level, we can, because we have agreed on that reference level of 20 micropascals that equals 0 dB SPL, now we can talk about, we can use decibels to talk about actual sound pressure values. So when I say that is 100 dB SPL, that represents an actual pressure, right? There's no, because the reference is implied, the comparison is implied, the comparison of 0 dB, okay? But it gets a little dicey when you start thinking about it per frequency because of our hearing system, which is not sensitive in the same way to every frequency. So we are less sensitive to low frequencies than we are to high frequencies. The reason for that, by the way, is that, notice, the area where we're most sensitive is this area between like 2 to 4K. Oops, come back. There we go. From like 2 to 4K. The reason that is that those are the frequencies that contribute most to intelligibility, speech intelligibility. Okay, so our hearing systems are naturally predisposed to being able to, because the primary function of our ears is to allow us to communicate with one another, right? So I can speak and you can hear and you can understand what I say. Okay, so our ears are pre-tuned for speech. Okay, so we're super sensitive to that 2 to 4K range that is so critical to speech intelligibility. We're much less sensitive to lower frequencies because those don't have anything to do with intelligibility. In fact, those can kind of hurt intelligibility if you let them get out of hand. So you've got to, if you want these low frequencies to sound just as loud as the higher ones, you've got to really boost them. So if we go back to that 100 dB SPL, if you want it to sound like 100 dB SPL at all frequencies, you can't be shooting out a flat frequency response. Okay, you've got to be curving it quite a bit in order to make it sound as though every frequency is that same level. And that sensitivity changes with pressure. So just to further complicate the issue, when we get to lower sound pressure levels, that differential in sensitivity is very steep, very dramatic. Okay? But when we get to higher levels, our sensitivity flattens out a little bit. Okay? And you can kind of see that as you look at this graph. So as we get higher and higher and higher, the flatter this curve gets. Okay? So then we were looking at this, and this is essentially a frequency response graph of our hearing, okay, at various levels. So this blue line, the A line, that would be the frequency response of our hearing at very quiet levels, very low sound pressure levels, okay? And by low, I would say anything below 60 to 70 dB SPL-ish, okay? Now, when anywhere between that 70 to 90 dB SPL is probably closer to the B weighting, okay? This is how you hear, okay? So if you got sent a flat sound, it would sound like this response to you. Now, when you get up past around 90 to 100 dB SPL, it flattens out quite a bit and starts looking more like that red line. That is the response of our hearing. Why does this matter to you? Well, because it comes into play in a couple things. So I'll give you an example that I've been wrestling with all weekend. So I'm doing this show. It's a Bob Marley musical. Okay, so it's a piece of musical theater using Bob Marley songs. Cool, right? I got a 7-piece reggae band on stage, and I got 6 actors on stage, and they do dialogue scenes, and then they sing, They sing these Bob Marley songs that are interwoven into the story of the show. And in some cases, they do dialogue that's underscored by, these Bob Marley songs. And I have been having a heck of a time getting their mics tuned. Because, listen, when we go to, when we go to Ridin' High, for example, I want that to be a big, loud song, right? That's a big, fast, loud song, right? So I'm boosting the band, I'm boosting the vocal mics, and their mics sound, the frequency response of their mics just sounds really weird when I get to those high frequencies, or those high levels. And when I go down to dialogue, it sounds different. So I tune their mics, right? So I'll EQ their mics when they're speaking dialogue, and it sounds great. And then I get to the song, Ridin' High, for example, and everything goes up 15 dB in level. And suddenly those mics don't sound like they're tuned as well anymore. Why? Because we're louder, and the response of my ears has changed. So my sensitivity has changed. We've got that big of a differential. So what do? Well, I just have to kind of tune it for the middle, kind of the middle of that range, and hope that, it's, when you go quieter, that it's a little bit off, and when they go loud, it's a little bit off. And if anything, I'm tuning it more heavily towards the low level, because of the high level, I can add reverb, and that kind of smooths things out a little bit too. Yeah.
What prevents you from just making a separate scene and making it a cue?
Time. Time and expertise of the person mixing and rehearsal. I mean, that's a lot of cues to add, and a lot of buttons to push moment to moment through the show. Yeah.
So A is basically, at least the way you're talking about, A is the speaking dialogue parts, and C would be the singing. That's the difference between.
Yeah, basically. So it's almost like, I'm never getting to that. I'm never getting past 90 dB on this show. So I'm probably never really hitting the C. But I'm going from A to B for sure. Okay? And it's just weird. Yeah.
This may be a feedback thing, but is this the reason that you set your mix,
Mm-hmm.
and then if you just, so say you have like, your stereo out, and that's how it's all set up, and so you set your mix, and then if you were to push that up 60 feet, it sounds like it's unmixed. It sounds like it doesn't sound the same, just louder. It sounds different. Is that because of this?
Probably. I mean, the other thing that happens is, and this is the other part of what I'm wrestling with is, if I just turned the sound system off, we would still hear plenty, right? I mean, the band's in the room, they're on stage, the singers are on stage. If I just shut everything off, we would still hear stuff, right? And so a lot of the problem we're having is that what's coming out of the loudspeaker doesn't sound exactly like what's happening naturally in the room, okay? And so there's a differential there. And so sometimes that differential gets more obvious the louder you have the sound coming out of the loudspeaker, right? That's when you notice more the difference between the natural sound and the amplified sound. So that could be part of what you're experiencing, is that it's like, oh, essentially at lower levels you can be a lot lazier in your mix and your tuning, because half of what we're hearing is not you, right? So when you get real louder, then most of what we're hearing is coming out of the loudspeaker, but we still have that reference of the natural sound. So you have to tune a little bit tighter, and you've got to be much closer to making it be right, because you're hearing more out of the loudspeaker. So that's part of it, but some of it is this. Ian, you had a question?
Well, I was going to ask that, do you think that, is that all just this problem, or is that also related to coloration from using hardware to deliver the sound?
Well, I mean, so I'm using, this is one way that an equalizer can help you, right? Is as the sound comes into the mixing console, or the processor, or the whatever, you can shape the frequency response of it to correct whatever you need to correct for. For example, maybe the mic placement is weird, and so you're picking up a wonky response anyway because of where the mic is. And you can correct for that in the mixing console to, you know, correct up that frequency response. But then also you got to, then that sound hits the air and hits your ears, and depending on how loud that is, you know, the way you hear that balance of frequency is going to change. So you're correcting for lots of things. So yeah, some of that weird coloration is what's happening in my processing, but that's also kind of the point, right? So the processing, you know, perhaps maybe a better answer is that if you do the processing well, then the processing helps you, doesn't hurt you, right? So if you are lazy with your EQs and all of that kind of stuff, and don't do your ear training, and you're faking it, then you're going to notice a lot of problems when you start bringing things up louder, because it's like it doesn't sound right. So you can help with that, but just the point that I'm trying to drive home here is that something that sounds balanced across the frequency spectrum, that is a moving target. Okay, trying to hit that is very difficult because it moves all the time. And these are averages, by the way. So, you know, everyone's sensitivity is slightly different for frequency. So, you know, it's a very difficult thing to hit. So you just do your best. And I think that's one of the things that I consider to be my job when I'm in the room on a show is I am the ears of the show. Right? So the show sounds the way it sounds because the way it sounds is what sounds good to my ears. But, you know, if my ears are crap, then the show is not going to sound good to everybody else, right? So hopefully I've got really good ears. I take care of my ears. I don't abuse them. I haven't, you know, I haven't experienced a whole lot of really dramatic, you know, damage to my hearing. I do a lot of ear training so that, you know, the show sounds good to my ears and my ears are a good reference. Okay? Because that's all you can do. You can't like take, you know, a poll of everybody in the room and try to figure out how to make the show sound better, because everyone's going to hear it slightly differently. Okay? And not everybody knows what they're listening to either. They don't understand. And so you've got to be the one who has the good ears that, you know, you understand what you've got to do, and you know your own hearing, and you've trained it, and you've got a good tool there, okay? Here's the other place that this issue comes into play is when you start talking about noise exposure. So a lot of live venues and cities and communities and things will have noise exposure laws, okay? Nuisance laws and things about how loud. So it's how loud is too loud for your neighbor's party, right? Or how loud is too loud for the concert venue that's across the street from the community, the housing development. Or how loud is too loud for, you know, safety from the point of view of your audience and maybe hurting their ears, okay? So all of these laws there's a lot of laws and a lot of policies and things that are written about that to help regulate those kind of things. And in order to really make those things work well, you have to consider this issue of sensitivity per frequency, because depending on the actual pressure level, the perceived loudness is going to change given per frequency. Like here in Forsyth County, the noise nuisance law is horribly written. It basically, it's just impossible. It's impossible to conform to it, because the way it's written just says, if anyone is annoyed by the noise that you're making, you are in violation of the noise ordinance. Exactly. So it's like, how do you enforce that?
I think Nick's voice is annoying. Let's call the cops.
Right? But that's it. Like, that is how it's written. It's just like, if anyone calls and complains about the noise that you're making, you are in violation of the noise ordinance. It's like, that's stupid. Like, like that is a really poorly written policy there. So here's a better written one. You shall be found, you know, to be in violation of this county noise ordinance if the noise you're generating registers as higher than 60 dB SPL A-weighted at the listening point of the person complaining.
Good call, sound designer.
Right? So the point there is like, okay, it may very well be 90 dB in your venue, okay? But that doesn't mean it's 90 dB at the person's house that is, 300 yards away. Because, as we know, sound gets quieter with distance, right? So this person who's calling and saying it's too loud, well, how loud is it for them? Okay? And so if the cops show up and they measure your show and they say, wow, you're 90 dB. This is too loud. You were in violation of the noise ordinance. It's like, well, wait a minute. Who are we disturbing here? Right? The person across the street. Let's go over to that person's house. And let's measure it at their place, in their living room, where they are sitting and being annoyed. And let's see what we're really doing here. And if you have your SPL meter and it's set to C weighting, that meter is going to register a higher level. Okay, because, think about that for a moment. It's the low frequencies that are the harder to stop, right? We learned that. If you want to stop a frequency, you've got to have an obstruction that is larger than the wavelength of that, right? So it's much harder to stop the low frequencies, and therefore the low frequencies are the ones that travel farther. They tend to still be there when you go a long ways, and the higher frequencies go away. So the person far away is probably hearing more low frequency than high frequency. Yeah?
So at my house, at my mom's house, we can, if you're in the driveway on like a Friday night, you can hear the Mount Tabor football games.
Right.
Live like a mile away.
Yeah.
If it was completely flat between me and Tabor, and you could only hear, you could just hear like the thump of like the drums every once in a while and stuff. If we were completely flat, absolutely no obstructions, would you hear the whole thing, or would the high frequencies?
No, because there's still temperature and wind and.
Why? So if there's like no obstructions, then what is the reason that the highs don't go as far?
Because of temperature and humidity and altitude, and there's a lot of things that affect this. So the obstruction is just one example of why low frequencies are harder to get rid of than high ones. So it's a lot harder to shoot a high frequency 500 yards than it is to shoot a low frequency 500 yards. It's just harder. It's just harder to get it to still be there by the time you go that distance. It's just hard. Yeah.
So like if you're in a venue and so since low frequencies are harder to get rid of, and let's say you're in a venue and you're doing a show
Yeah.
and a train comes through town, how would you try to keep like rumbling of a train going through town out of your show?
You can't. I mean, you can't. There's just like, So what the thing I'm trying to get at is, if in that case of the noise ordinance violation, if you go to the person's house that's complaining and you have an SPL meter and it's set to C weighting, well, by the time they've gotten far away, it's not 90 dB anymore. It's quite a bit quieter. It's probably closer to 60 dB SPL range, okay? And so if you have your meter still set to C weighting, you're going to register a higher pressure level, right? Because C weighting is not attenuating for low frequency. But when you get down to that 60 dB SPL, which is probably closer to what it's like at that person's house, at that point, what that person is hearing is closer to this A-weighted response. And so you want to switch your meter to A weighting, because then the number that you see on the thing reflects the loudness that the person is hearing at the place where they're sitting. Okay? And if you're at A-weighted and it still says you're higher than whatever the noise ordinance is, then okay, you're in trouble. You got to do something about that. But so now, if you're in Forsyth County, it doesn't matter. It's like somebody complains, you're done. You could call Mount Tabor and shut them down if you wanted to.
I have a feeling those laws are left open on purpose, and not so much for like rock concerts, but more for like house parties.
Oh yeah, absolutely. But what I'm saying is that that makes it essentially impossible to correct the problem, right, when it's written that way. So, you know, of course you don't want to be a nuisance to people. You don't want to do that. But how exactly are we to correct this problem, right, short of shutting down the performance? Right? What, you know, what is the line by which we can cross in order to not be in violation anymore that still allows us to do what we got to do, you know? So if it's really poorly written like that, like it's really difficult. It's really difficult to fix the problem. So that's just something to watch out for. And you'll notice if you've ever played around with a sound pressure level meter, you can get them for your phones. You can get standalone ones. There's usually a thing for weighting curves, and that's what that's about. So usually you don't see the B weighting so much. I don't know why, but you don't see that as often. You'll usually see A or C. So my rule of thumb is, you know, if it's 80 dB or less, use A weighting. If it's more than 80 dB or so, use C weighting, just so that what you're measuring is closer to what your ears are hearing. Okay? So remember that, and remember this dB SPL. When we say dB SPL, we're talking about decibels referenced to what? Sound pressure level, which is, and what is the reference level for that? 20 micropascals. Okay? 20 micropascals. So when I say it's 100 dB SPL, I mean it is 100 dB more than 20 micropascals. Okay? So that is one example of how, if we can just agree as a professional community on a reference point, then we can start using decibels, which is normally a relative value. We can start using it like it's an absolute value, if we can somehow agree on the reference point. Okay? Here's another one, dBV. dB with a big V. The V stands for volts. So these are decibels referenced to 1 volt. This means that 0 dBV equals 1 volt. You'll primarily see this in what I call consumer audio equipment. This is like the kind of stuff you would get at a Best Buy or something. It goes in living rooms. Usually has like RCA connections on it. Unbalanced signals usually, which we'll talk about in a minute. So dBV. And there's like the nominal operating level for consumer level stuff is minus 10 dBV. And by nominal, what I mean is, you know, what comes, if you just take whatever the source is and shoot it straight out without any attenuation or amplification, what comes out of that connector will be minus 10 dBV. That's minus 10 dBV is 0 on the meter, unity on the meter for the device. Okay, that'll be minus 10 dBV. And we'll do some, you can calculate that actual voltage if you want in a minute. Because this is voltage, that means it's a force, and therefore dBV follows that 6 and 20 rule. So you double the voltage, you go up 6 dB. Multiply the voltage by 10, you go up 20 dB. So dBV. So anytime you see a value that says, you know, like minus 10 dBV, that means this is 10 dB lower than 1 volt. And again, this is not open for debate. This is just one of those, this is an industry standard reference level. If you want to be a professional sound person, you just have to agree with this. You have to agree that 0 dBV equals 1 volt. If you don't agree with that, you don't get to be a professional sound person. Okay? Because that's the only way that it means anything, is if we all agree on the reference level. Okay? If, you know, North Carolina says it's 2 volts and South Carolina says it's 1 volt, then we can't do sound together. Okay? Because it just doesn't work that way. So here's another one, dBm with a little m. The little m stands for milliwatts. So this is decibels relative to a milliwatt. So 0 dBm equals 1 milliwatt, or 0.001 watts. So this is you'll mostly see this one specced out when you're talking about wireless transmission levels. So like your wireless microphone transmitters, let's see, Wi-Fi transmissions are usually measured in dBm. As far as like the amount of gain you get out of an antenna, for example, or it'll say X number of dBm. The nominal levels for this vary, depending on what equipment you're talking about. There's not like a real standard for that. There used to be, but not so much anymore. Because this is power, watts is power, so this follows the 3 and 10 rule. So you double the power in milliwatts or watts or whatever, you will get a 3 dB increase. Multiply that power by 10, you get a 10 dB increase. So that's dBm follows that rule. So you might see this if you look at specifications for, like your wireless mic transmissions. You might actually see this thing will put out a certain number of dBm, and that'll mean an actual amount of watts of RF power. So again, just have to accept that 0 dBm equals 1 milliwatt. There's no reason for that other than that's what we decided. So can you all get aboard that train? Yeah? Okay. All right. You have to, or you don't get to be a sound person. There's another one called dBu, little u. The U stands for unloaded. And what that means is, it used to be that in the early days of audio systems, before we started figuring out that we could standardize things, input impedance for different devices in an audio system, that was a bit of a moving target. Like you never quite knew what the input impedance was. And therefore, there was this whole process called impedance matching, where you had to figure out how to match the impedances of the devices you were connecting in order to allow really efficient energy transfer. It's not very fun. And so instead now, in the professional world, and dBu is the professional low voltage audio standard. So the 0 dBu equals 0.775 volts. And you're probably thinking, 0.775 volts, seems like an awfully weird number to use as a reference point. But here's the reason why, is that if you take 0.775 volts and put it into 600 ohms, that is 1 milliwatt of power. So 0.775 volts pushing against a 600 ohm impedance will perform 1 milliwatt of work, which is coincidentally equals 0 dBm. So dBm was around before dBu. Yeah?
Why 600 ohms? Cool. Because they said so.
Well, I think it was well, I don't know, but essentially they wanted a really high impedance because that means that the voltage that you're feeding into that is usually going to be really low voltage and very low impedance on the output. So outputs are usually not 600 ohms. Inputs are. And the reason is that if it's a really high input impedance, then you've got really consistent and efficient energy transfer. Imagine like, the garden hose of water when you stick your thumb over it. You are increasing the impedance, right? And when you increase that impedance, that water starts zoom, really shooting out of it, right? That's what we want to have happening with our low voltage audio signals. We want really efficient energy transfer go into this thing. So we go really high input impedance, and that means that we could take the output of something and we could split it lots of ways, right? You can do Y cables, we can do mults and patch bays, and we can take that signal and split it as many ways as we want, and we don't usually lose a whole lot because that high input impedance allows for it, for that energy to really spray right into the next thing. So even if it drops a little bit, it still comes in pretty well. But the reason you have 0.775 is because of this interesting little mathematical equation, because we used to think about all this stuff in dBm. And to try to maintain that reference level for dBm of 1 milliwatt, they came up with 600 ohms impedance for some reason that I don't know, but they just needed a high impedance, and that was a nice round number. And so that got them 0.775 volts. 0.775 volts into 600 ohms gets you 1 milliwatt. Yeah.
It's probably off topic, but going to the ohms, the resistance. So if having a higher impedance means that it's more efficient energy transfer, why do we have such low impedance for speakers? Because wouldn't you want them to?
Because those have to move a lot heavier of an object, right? So a loudspeaker has to move a big thing. And we're talking about moving a little teeny tiny thing inside of a line level device. Yeah.
Maybe this is a false equivalency, but I understand how it benefits us that we have standards for consumer and professional line level. But are there companies that realize that if they make their equipment sound better with their own equipment, that they'll sell more units or more peripherals?
What do you mean?
Maybe I'm equating with having a standardized professional and consumer line level with something else. But if you have it so like the impedance on your devices is set to only work with your devices, wouldn't you theoretically sell more units? If it's this company's unit and it sounds best with another.
Yeah, I mean, we went down that road for a while, and ultimately, that didn't get us very far, because it's like not everybody can do everything well, and so, the industry demanded that we standardize this stuff, because it's like, listen, I don't, I want to pick the best mixer and the best loudspeaker and the best amp, and the best, whoever's got, and they should all work together, right? And so that's why organizations like Audio Engineering Society exist, IEEE. I mean, these are all things that help standardize things, and it's usually in manufacturers' best interest. I mean, yeah, everyone's going to have their little secret sauce that they add to it, but if they're not following industry standards, they're not going to get very far, because it's like very rarely are you going to be in a situation where you can buy whatever you want, right? You're going to get what you get. It's either this is what the shop has, or this is what's in the venue, and you're cobbling a whole bunch of disparate things together, and if everything's talking a different language, it just doesn't work. And I think that's kind of where we are right now with digital communication between devices. We haven't fully standardized all that stuff yet, and so you've got all these different digital formats for passing audio, and it's a mess right now. It's getting better. We've gotten a long way in the last 5-6 years, but it's still all over the place. And I think eventually it'll be standardized. Doing digital audio transmission over a Cat5, for example, will be no more complicated than an XLR currently is. So, but we're just not there yet, and it's a nightmare. And the industry is demanding. I mean, the end users, are demanding that we get this stuff standardized. It's like, this is a headache. We can't be spending hours and hours and hours on every show just trying to get all the boxes to talk to one another. This has to be simpler than this, okay? So the end users don't want that, so they're not going to buy it, So the reason that unloaded is the word here is because by standardizing the input impedance of the line level devices, then you don't have to worry about the load anymore, okay? You don't have to worry about that input impedance, because that's standardized. And so now we can start talking about it in terms of voltage as opposed to power, which is a lot easier to work with. So that's what the U is, unloaded. dB unloaded means standard input impedance of 600 ohms, and the 0 dB, or the nominal operating level for that, is 0.775 volts, because they were trying to compare it to 1 milliwatt, okay, or 0 dBm. Now, for professional devices in dBu, plus 4 dBu is usually the nominal operating level. What that means is when you see the meter hit 0 on the device, that means it's probably hovering at, that voltage is plus 4 dBu, which is about 1.23 volts, okay? You can, of course, go higher than that. You can go lower than that, but usually that unity gain is going to be plus 4 dBu. It's voltage as well, so it follows that 6 and 20 rule, just like dBV. There you go. That's just one you gotta accept. All right, let's see. Oh, here's another one, dBW. You don't see this as often anymore, but this is a capital W, 0 dBW equals 1 watt, okay? So you might see this sometimes spec'd for power amplifiers every once in a while, dBu. The reason you don't see it a whole lot is because when we start talking about watts and power amplifier output, it's usually, we're not talking about a huge range of values. You know, we're usually, you know, between 1 watt and 1,000 watts most of the time. And that's not a huge number to deal with. Every once in a while, you know, you'll get into some larger numbers, but the absolute highest number I've ever really had to deal with a power amplifier is 10,000 watts, and that's rare. So those are not enormous numbers. That's not like the difference between 1 and a trillion. Okay, so that shortcut of sort of collapsing this wide range into dB is not as helpful when you're talking about really high power output levels for amplifiers, because it's not a huge range you're dealing with. But it is possible to do it, and I have seen it from time to time on specifications, because there are some manufacturers that I believe rightfully so feel as though, you know, marketing departments have just completely taken this concept of watts and made it meaningless. You know, it's just stupid. And I've heard our own students in this very room talk about it that way. Like, well, how many watts is that? You know, how many watts is that speaker? It's like, it doesn't matter. That doesn't mean anything. The number of watts, it doesn't mean anything all by itself. That does not turn into sound. You know, there's no direct equivalency to the number of watts and the amount of sound that generates. Okay, there's no direct connection, because there's a device in between that called the loudspeaker driver, and that driver is going to each loudspeaker driver is going to do a very different thing with that same amount of power. You could put 100 watts into one loudspeaker and only get 60 dB SPL. You could put that same 100 watts into another loudspeaker and get 100 dB SPL. And that's a huge difference. So the watts are not particularly relevant in and of themselves. Yes.
I know generally I know in guitar amps, and that's where I come from, but I know that the number of watts doesn't necessarily deal with loudness. It deals more with the headroom before the amp starts breaking up. Is that the same here?
No.
Okay.
That's actually not what it means.
All right.
Again, it's marketing.
Gotcha.
It's like the number of watts in the guitar amp doesn't mean anything.
So why does like a 15-watt amp break up quieter and easier than a 45-watt amp?
It has everything to do with the driver that's in there.
Okay.
It's a far more complex problem.
Gotcha.
And because of that, I mean, I understand that. Like, if I'm a marketing person and I'm trying to give people a reason to buy this product over another one, you know, the difference between these two products is complicated. It's a complicated electrical circuit. And you've got to collapse that into like a 3-word byline in an ad. It says, buy this because it's, you know, you only get 3 words after that before people start tuning out, you know? And what are those 3 words going to be? You know, it's either you either just pick some arbitrary feature of it that sounds impressive, or you make stuff up, like.
It's a bedroom amp.
Yeah, it's
cleaner, louder volume.
Yeah, it has extra pure dilithium crystals. You know, I mean, so you either make stuff up, or you find some arbitrary true thing about it that you can fit into 3 words that sounds dramatically different from something else, and you put that into the headline, and that usually is watts, right? So it's like, this one is 100 watts, this one is 50 watts. 100 watts must be better because it's bigger, right?
The 100 watt speakers, the sensitivity on the drivers is way lower. And
Yeah.
higher impedance.
Yeah, exactly.
So it doesn't matter.
Doesn't matter. You might get the exact same actual sound output out of both of them, right?
It doesn't matter unless you know everything else.
Yeah, exactly. It's like that. That is, just saying the number of watts. That is not giving you a complete picture, right? There's far more going on in there that before that turns into sound that you hear.
I feel
Okay.
like our audio really uses that to their advantage.
Oh yeah. Oh yeah.
A lot. That's really what they advertise as.
But think about it. 50 watts to 100 watts. What's the dB difference there? Let's assume that everything else about the two amplifiers is the same. What is the difference going to be in sound output between those two amps? 3 dB, which you can barely hear. And so if there is a dramatic difference between those two, it's not because of the power difference. Because if the power difference was the only thing different about them, then you would barely hear the difference between 50 and 100 watts. So if there's a dramatic difference between the 50 watt and 100 watt, there's a lot more going on inside that 100 watt amp than just the power. Okay? There's a lot more going on because just doubling the watts alone does not get you a dramatic change. It gets you a change you can barely hear if you pay close attention. Right? Okay. So what I was getting at is there are some manufacturers that have successfully convinced their marketing departments to stop doing this, and they'll start talking about this in terms of dBm or dBW. To try, because if you talk about it in dBW, then you could say, instead of saying 50 watts versus 100 watts, you're saying 60 dBm versus 63 dBm, right? And if the 63 dBm is $3,000 more expensive, and you see well, there's only 3 dBm difference between them. What else is going on here? You're more likely to pay attention to the other details, right? If you don't have this huge number being thrown at you. So I think that's much more responsible, personally. A much more responsible way to market your product. But it requires more of your customer. You have to assume your customer is smarter, because maybe you shouldn't assume that. I don't know. I appreciate it though. When I see much more purposeful marketing like that, I appreciate that. Okay, so let's do some math on this, shall we? I don't know why my thing is. Okay, so how many volts is minus 10 dBV? Remember I said that minus 10 dBV is the nominal operating level for consumer equipment? Remember I said that?
Yes.
Yeah, I said that, right? Okay, so how many volts is that? How might we figure that out? Well, the first thing we would need to know is the force ratio of minus 10 dB. Right? And that can be calculated using 10 to the power of negative 10 divided by 20. Right? So let's take a look at how you might do that with the calculator. So here's my calculator. And I'm going to do 10 to the power of negative 10 divided by 20. So I'm going to first type the 10. And then you should have a little number on your calculator, a plus/minus. I'll hit that. So now I'm dealing with negative 10. So I'll take negative 10 divided by 20. And I get negative 0.5. Okay? And then you should have on your calculator a little 10 to the power of x button. And that just, the x gets replaced by whatever value is currently on the screen. So I hit 10 to the x. I get 0.316. Now, that is the force ratio for minus 10 dB, which means I can take this number and multiply it by some other force, in this case voltage. So I could take this number, multiply it by any voltage I want, and I will get a voltage that is 10 dB lower. Okay? So if I want to know how many volts is minus 10 dBV, I just take this number and multiply it by the reference level for dBV. And what is the reference level for dBV? Say it again, Dan. 1 volt, right? So 0 dBV equals 1 volt. So I take this number, this force ratio for minus 10 dB, and I multiply it by the reference level, 4 dBV, which is 1 volt. So I say this number times 1 volt, and I get 0.316 volts. So that minus 10 dBV, which is the nominal operating level for consumer-grade equipment, is 0.316 volts. That's something you probably ought to just memorize. 0.316 volts. So 10 to the power of negative 10 divided by 20 is 0.316. And you divide that, or multiply that by the 1 volt, which is that reference level, 4 dBV, and you get 0.316 volts. So
I thought the reference relevant was the 0.775.
that's for dBu.
Oh, I'm seeing that looks like I read it wrong.
Okay? So 0.316 volts. So when you're dealing with a consumer-grade piece of equipment, and the way you know it's consumer-grade is usually the type of connections that are on the back. So if it has RCA connections on the back, pretty dead giveaway that that thing is going to be a consumer-grade thing, which means when the meter on that thing lines up at unity, you're going to get 0.316 volts out of it. Okay? We'll talk about in a minute why you should care about that. But for now, just memorize that. Memorize the consumer-grade equipment is 0.316 volts nominal operating level, minus 10 dBV. Okay, what about professional equipment? Remember when I said that professional line level is plus 4 dBu? I did say that. So how many volts is that? Well, it's the exact same problem. Okay, so I just need to know what is the force ratio for plus 4 dB. That's the first thing I want to figure out. So that's going to be 10 to the power of 4 divided by 20. Somebody want to run that for me? 1.58. Did anyone else get that? So 1.58. So that is our magic number. I can multiply any voltage by 1.58, and I will get a voltage that is 4 dB higher. Okay? So if I want to know how many volts is plus 4 dBu, I just have to multiply this number by the reference level for dBu. And what is the reference level for dBu? 0.775 volts. What does that equal? Should be 1.23 if you round up, right? 1.23 volts. That's another one you ought to memorize. So what that means is on your professional mixing console that has an XLR output on it, if you hook a little voltmeter up to that XLR output and you put a signal through your mixing console that lights up the output meter at 0 dB on the meter, unity gain on the meter, you will get 1.23 volts coming out of that XLR. And that's a very low voltage, right? So we call, most of our audio systems now are low voltage systems, we call them, which means we don't have to follow all the same electrical codes that you have to follow when you're talking about high voltage stuff, which is helpful for us. All right. So here's an interesting one. How many dBu is minus 10 dBV? So the question is, the scenario where this would be important is, what if you're going to plug that consumer level piece of equipment into your professional mixing console? And you know the nominal operating level of that consumer thing is minus 10 dBV. Well, what's that mixing console going to see that as, since your mixing console uses dBu? Okay? So we start, again, by getting the force ratio of minus 10 dBV. So that would be 10 to the power of negative 10 divided by 20, which we know is already 0.316. Okay. So if that's volts, so 0.316 volts, and I want to know how many dBu that is. So remember, this is the magic number. I multiply any voltage by this, and I will get something that is 10 dB quieter. So all I really have to do is multiply this by the reference level for dBu. right? So this is actual volts now. So multiply this by the reference level for dBu, which is 0.775. And what do we get?
0.245.
Oh, I'm sorry, dB, no. Hang on. Yes, 0.245 dBu. Which is not a whole lot. Okay, here's another one. How many dBm is 0 dBw? Well, I first would like to know how many watts 0 dBw is. So how many watts is 0 dBw? All right, so 1 watt is what I'm working with here. And if I want to know how many dBm that is, you know what? I want to go back to that last question after this because I realized why I was stumped on that. I think that was wrong. I understand now why that was wrong. So give me 1 minute. We'll do this one, and then you'll see why. Okay? So it's 1 watt, and dBm, the reference level for dBm is how many watts? 1 milliwatt. So 0.001 watts. Okay? So those are 2 power levels, right? Okay? So if I want to know how many dBm is 1 watt, I can just do 10 times the log of. So if I were to express dBm mathematically, it would be dBm equals 10 times the log of x divided by 0.001. That is dBm, right? You know what I did wrong about the last one, right? All I got to do to get a dBm is I just substitute some power level for x, and I will get that power in dBm. So I just put a 1 in for x, which is my 1 watt. So 10 times the log of 1 divided by 0.001, and what do we get? 30 dBm. Okay, so 0 dBw equals 30 dBm. Yeah? Okay, so let's go back to the one before because I did that one wrong. Okay, so we know, let's go back. We know that minus 10 dBV is 0.316 volts, right?
Yes.
We know that because we already figured that out. dBu, mathematical expression for dBu is dBu equals 20 times the log of x divided by 0.775, because 775 is the reference level for dBu. Okay, so I did that. When we did it before, I did it backwards. Sorry. So all I got to do is take this voltage value and put it in for x. I thought that number looked funny when it came out. So 0.316, 20 times log of 0.316 divided by 0.775. What does that equal? Somebody do that.
-7.79.
That sounds more correct. dBu. So minus 10 dBV equals 0.779 dBu. That makes more sense to me. Okay, that's correct. Mm-hmm.
So, the reason V is 20 log is because it is power, or because it is
Voltage, and voltage is a force, and therefore you used.
force, and then
Yep.
the reason watts is 10 is because it's power.
Mm-hmm. Yep. Okay. Okay, did that one. All right, so here is the take-home message here. What is the dB difference between plus 4 dBu and minus 10 dBV? Those are the 2 nominal operating levels, right? Plus 4 dBu is the nominal operating level for professional equipment. Minus 10 dBV is the nominal operating level for consumer-grade equipment. So what I want to find out here is, let's say you have, I'll say a CD player because that's an easy example. So you've got two CD players. You could simulate this experiment in our shop if you wanted. We have some CD players that are professional operating level and some CD players that are consumer operating level. If you put the same CD in both of those CD players and plug them in to your professional mixing console, what would the dB difference be between them? It's the same CD. You're not doing anything different with the gain knobs or anything on the mixing console. There will be a difference in output between those two things because consumer-grade equipment outputs a lower nominal operating voltage than professional equipment does. Right? Professional equipment does 1.23 volts nominal. Consumer-grade equipment does 0.316 volts nominal. That means on that CD, exact same CD, whatever loudness level that those bits turn into, whatever that nominal level is, that 0 on the meter, that comes out as two different voltages on the two different players, even though it's the same CD. Okay, so what is that dB difference? You get a question?
Why do they have a different dB, a voltage for consumer and professional grade? It's not like a big difference. Why don't they use
So some of it has to do with balanced signals, because that's a big difference between consumer level stuff and professional level stuff. Is in professional world we like to use balanced signals because we're running our cables a lot longer distances. You know, in your living room, your cable's a couple of feet, between devices, and that's not enough distance to really pick up a lot of noise or interference on that cable. But in the professional world, we're running hundreds of feet, and so we tend to want to use balanced signals because the balanced signal is much better at rejecting noise and interference. And a balanced signal will inherently be a higher voltage because you're sending the signal down twice and then summing it together. Okay? So it's always going to be a higher voltage no matter what. So that's a big part of it, is the balanced signal. It also has to do with what we were talking about earlier. It was just that comparison of milliwatts to dBu when you start standardizing that input impedance. They were trying to hit that 1 milliwatt value because that's what we were dealing with before when we sort of standardized dBu. So they ended up with a higher voltage because they were trying to make it be a comparison to dBm. Okay? So what is the dB difference between consumer level stuff and professional level stuff? Well, all we got to do is convert these things down to their actual voltage levels, which we've already done. So what is the voltage value of plus 4 dBu? 1.23 volts. Okay, and what is the voltage level for minus 10 dBV? Yeah, 0.316 volts. Okay, that's two voltages. How would I figure out the dB difference between those two voltages? How do I find the dB difference between two voltages? Yeah, so what's 20 times the log of what? Yep, 1.23 divided by 0.316. Somebody do that math, tell me what the answer is. 11.8 dB. Otherwise, you could round that to 12 dB, and it'd be about the same thing. So, what's that? Pretty big difference, right? That's a difference you could hear. So, in that, back to the scenario of the CD players, two CD players going into your mixing console. One is a consumer level one is a professional level one. Put the same CD in each one. Maybe one's your backup or something. Well, that consumer level one is going to play that exact same CD into your mixing console 12 dB quieter. Okay? That's not necessarily a problem as long as you know about it. Because how could you correct for that? Because ideally, when you flip over to your backup that's on the consumer grade thing, you don't want the show to suddenly be 12 dB quieter, right? So how could you correct for that? No, I mean, just on your mixing console. What sort of things you can turn knobs and push buttons on mixing consoles to like fix stuff like this? I would just turn the gain up 12 dB on the channel that has the consumer level input into it. That's what that knob is for. That's what the gain knob is for, is to line up input levels, to get them all, maximized for your input gain. So I would know that right off the bat, whatever input is listening to that consumer level CD player, I got to turn that up 12 dB no matter what, because it's going to put out a 12 dB quieter signal than the other CD player. Okay? So if you know that, then you can correct for it. Yeah? Okay. How many dBm? This is not a particularly practical question, but it does make for an interesting little equation. How many dBm is a 300-watt amplifier? Well, like I said, we tend to use dBm to talk about things like wireless transmission levels, because those are usually very low power. And a 300-watt amplifier, that's a very high power output. So not a particularly useful conversion, but it's fun to do anyway. So remember, what is the mathematical definition of dBm? dBm equals well, 0 dBm equals 0.001 watts, but dBm in general. 10 for power. 10 times the log of x divided by 0.001, right? So we can take any power level, plug it in for x, and we will get that power level in dBm using this formula. Okay? So in place of x, we're going to put 300. So 10 times the log of 300 divided by 0.001. Anyone else get that? Yeah? Okay, as I say, that's not a particularly helpful bit of information, but it's a fun little conversion to do to kind of think about how these things are equivalent to each other. Okay. Yeah, we got time. Okay. Oh, any other questions about those reference levels? So the reason I'm having you do conversions between some of them is you can't always control what information you're given, right? I mean, somebody puts up that spec sheet and they put whatever information on that they feel like putting, and sometimes it's not the information you want, but you can usually get the information you want by converting whatever they gave you into what you need, okay? So usually if they can give you a couple of reference points, you can derive all the other information. Okay. Here's another kind of interesting phenomenon of dB, and this goes, somebody asked this question last time, and I said I'm going to answer it later, so I'm answering it now, okay? Which is that there is a misconception that is not an unreasonable conclusion for you to come to when you, but I want to make sure that we understand this, is remember, decibels are an approximation, and they are a relative level, right? We know that. And yes, we now know that we can use decibels to talk about absolute values, even though decibels technically are relative. We can use them in absolute terms if we can agree on a reference point, right? So, for example, SPL is a reference point. 0 dB SPL, we've agreed on a reference point, and therefore we can talk about dB SPL in absolute values. But that doesn't mean, just because those dB SPLs become absolute values now, that does not mean that they interact with each other linearly. They don't, because they are still approximations. They are still abbreviations. And what I mean by that is you could take two sounds that are making 90 dB SPL each. This could be two loudspeakers or two musical instruments or whatever. That does not, both of them together, each making 90 dB SPL, they don't combined make 180 dB SPL. if that was true, we would have a lot of deaf musicians, a lot more than we have right now. Okay? So two things creating, if they could both be creating the same dB SPL, but they don't sum together linearly. Okay? Turns out, and if you think about this for a minute, you'll realize why this is the case. Because remember, that dB SPL represents an actual pressure value. Okay? Because 0 dB SPL is 20 micropascals, and therefore 90 dB SPL would be some value in pascals. Okay? And when you sum those two pressure levels, so that 90 dB SPL represents an actual pressure level. So you've got two things exerting the same amount of pressure. What happens when you combine two pressure levels? How many dB difference do you get? That's not what I taught you. What did I teach you happens when you combine two forces? Pressure is a force. Double the force, how many dB? 6, right? Double the pressure, you get a 6 dB increase. Okay? It's a 3 dB decrease if you're talking about power. We're talking about pressure, actual pascals. So those two 90 dB SPL things are actually exerting an actual pressure. And what's really happening is that pressure is summing. When you double the pressure, you get a 6 dB increase. And now you're saying, but Jason, your slide says you get a 3 dB increase. So is that, yeah. So did I screw up? Or, no, I didn't screw up in this case. Here's why.
This slide just makes me think of 1984. +2 + 5.
Yeah. So think about this for a moment. Why am I saying here, why would I say that it's only a 3 dB increase when I just told you that when you sum two pressure levels, you get a 6 dB increase? Why does it say 3? Think about that for a moment. Remember, there's two answers to almost every question I ask you. Two possible answers. One of them is depends, and the other one is, okay, which is the answer to this question? Comb filtering. Exactly. Comb filtering is the reason. Okay? So yes, in a perfect scenario where everything was perfectly in phase and time aligned and everything, and there was no destructive interaction between these two sounds, then yes, you would get a full 6 dB increase. But in practice, these things are not existing in the same physical space. So these two musical instruments, or these two loudspeakers or whatever that are making the same amount of pressure, they're in two physically different locations, which means they combine in the air at different times, right? And time equals phase. And when you have phase changes between two sounds, destructive things happen. Some sounds cancel out, some sounds reinforce, some sounds do nothing, right? Comb filtering. Okay? So usually, when you have two things actually pushing on the air and making sound, you will get a 3 dB increase if they are both doing the same thing because of comb filtering, except for sub-bass. So when you get to really, really low frequencies, like 100 hertz and below, you will get 6 dB there. Why? Why? Why do you get 6 dB for the low frequencies, but you only get 3 for the higher ones?
It's because low frequencies are omnidirectional.
No, I haven't taught you about directivity yet, so it can't be that. Say again? Close. So the wavelengths are larger, right? So it takes for a low frequency, it takes a much longer offset of distance to create a cancellation. Okay? So unless the two things are really far apart, it's unlikely that the really low frequencies are going to cancel out. Okay? Because they haven't quite gotten to that 180-degree phase shift yet. But they only have to be offset by a few inches for high frequencies in order to create destructive interactions. Okay? However, the good news is we are less sensitive to low frequencies, aren't we?
Yeah. So
And therefore, it still sounds like it's only 3 dB. Okay?
So if you had two subsources, if they were far enough from each other, it would be. I'm trying to think if it would be 3 or if it would be 6.
Well, so there's a lot of folks out there that will spend a lot of time figuring this out, and you might have seen this maybe if you've ever been to like live concerts or something, where they've got like rows of subs across the front of the stage, all spaced apart. They're not touching each other; they're actually spaced apart. Why are they spaced apart? Because they are trying to create a directional sub bass. Okay, so they're purposely spacing these apart in such a way to create a cancellation on this axis for the subwoofers, so that they will stay off the stage. Okay, so you got the mic up here, right? And the subs are right there on the edge of the stage, and the mics are right here, which means here is cancellation. Okay, but out there, reinforcement. Okay, so you can get subs to be directional if you get a lot of them and space them out just right. But you need both a lot of subs and a lot of space to do this. So usually not very practical for small theaters, but large concert venue, big stadium, yeah. You usually have both of those things. Lots of money and lots of space. Okay. So here is another kind of little thing to keep in mind, is that if you get two sources that are combining 10 dB apart from each other, so maybe one of them is 90 dB, the other is only 80 dB, there is no increase in level, perceived level. That second thing may as well not even be happening. Okay? So why does this matter? I know, but it's true. It's true. So there's a couple of take-home messages here. Once the sound hits the air, remember, we're primarily tasked with making stuff louder. Once it hits the air, your ability to get it louder is really, really, really restricted, okay? Because think about it this way. Let's say you've spent $30,000 in a rental for a big sound system that you're putting into a space. You've got everything installed, everything's figured out perfectly, your sound system is well designed, you've got your gain structure perfectly lined up, you don't have any feedback that you're concerned about, you're putting out the absolute maximum that equipment is capable of generating. It is creating the most sound it's capable of generating because you did everything right. And let's say the show is still not loud enough. Okay? You could go and buy a completely second sound system, 2 of everything, and put that second sound system in the same room exactly the same way, turn it on, you would get a 3 dB increase. Okay? You could spend that $30,000 all over again and get only 3 dB difference. Because once it hits the air, it gets really difficult to make a difference.
But if everything was perfect, like phase and everything, it would be 6.
Yeah, if you could get, so you're going to buy 2 of each loudspeaker, right? If you could get the center point of each of those loudspeakers to somehow exist in the exact same physical space, like, the other one is in a different quantum dimension or something, then yeah, you could get a 6 dB increase. But you can't, right? You're going to have to put them next to each other. They're going to be a foot apart or something. And so they're going to come filter, and therefore you're only going to get 3. Okay? You're only going to get 3, except for sub bass, and you'll get 6.
Yeah.
Okay?
So in that scenario with a $30,000 budget to buy all that stuff, you would just have to save up and get better equipment, right?
Right. So again, if you've spent the $30,000, you've done everything right, everything's perfect, everything's perfectly configured and dialed in and gain structure and everything's great, and you still don't have enough sound, you bought the wrong stuff. Okay? You need something different. You don't need something more, you need something different. Because you could completely double everything you have, and you would only get a 3 dB difference. Okay? So buying a second loudspeaker is not necessarily going to solve your problem. Right? If one loudspeaker does not make enough sound, 2 loudspeakers is not going to make enough sound. Right? To make a noticeable difference. So in that scenario, 1 loudspeaker is not making enough sound. You buy a second loudspeaker, you get, well, let's say you got to make a 12 dB difference. Like you were 12 dB too quiet. You need 12 dB more sound. So you have your 1 loudspeaker. You say, oh, we need another speaker. It's too quiet. Get another one. OK, you're now only 3 dB louder, right? Still not at the 12. So if I buy a third loudspeaker, what do I get? Nothing is the answer to that question, right? You get nothing in that, right? Remember that 10 dB difference? So I've now got to get 2 more. So now I got 4. And now I'm at plus 6 dB from where I was before. Still not where I need to be. I got to buy 4 more. I got to completely double what I have. Now I got to go to 8 loudspeakers. And now I'm at 9 dB more sound. Still not there. So now I got to buy 8 more. So now I'm at 16 loudspeakers, and now I've created 12 dB more sound. And by the way, all those loudspeakers are exactly the same, and they're pointed at the exact same spot. That is not a very efficient way to get 12 dB more sound. No, that is not. Okay? So it's much better to get a more sensitive loudspeaker. Get a loudspeaker that's capable of generating more sound per watt of power. Okay? That's what you really want to do. But realize the same thing happens with musical instruments. Have you ever noticed, anybody ever seen an orchestra play? Okay. So let's just talk about the string section. Okay, there's 4 different instruments in a string section, right? What are they? Violin, viola, cello, basses. Okay. How many violins are there compared to how many basses there are usually in an orchestra? A lot more violins than basses, right? Why? Is it just because there's not as many bass players out there? Like, no. There's plenty of bass players out there, okay? It's not that. It's not that they can't hire the same number of bass players. It's because they don't need the same number of bass players. Here's why. The violin is quieter than the bass. Okay? So if that bass is, let's say the bass puts out 90 dB SPL on average, okay, and the violin puts out 75 dB SPL on average. So 1 violin plays, you get 75 dB SPL. 1 bass plays, you get 90. How many violins do you need for the violin section to be as loud as the 1 bass? A lot more violins, okay? So if I go to 2 violins, I would now be at 78 dB SPL, right? 4 violins would be 81 dB SPL. Still not there. 8 violins would be 84 dB SPL. 16 violins would be 87 dB SPL. 32 violins would be 90. 32 violins for every. Now, obviously, there's not that big of a differential between the violin and the bass. Okay? But there is enough that you need more of them, right? But it's a disproportionate amount more than you need, right? I mean, 16 violins is not unheard of in an orchestra, right? compared to maybe a couple of basses, right? So that's expensive. You got to pay every one of those people to show up and play. It's a lot of violins you got to pay to be there. So once the sound hits the air, it's really hard to make it louder. You could find a whole nother salary to pay a whole second violin player, and you're only going to get 3 dB more sound. Okay? So to try to make a difference, you got to make the difference earlier. You got to make the difference before the sound hits the air. Because once it hits the air, it's just impossible. Yeah?
If you have a distorted signal and a clean signal at the same level, why is it always that the distorted signal still feels like it's a little bit louder? Is it because due to the compression?
No, because it has more harmonics.
Okay.
All right, so the higher frequencies are louder, because a distorted signal just creates high frequency harmonics. So it's not that the whole thing got a whole lot louder. It's like parts of it got more louder,
Gotcha.
right?
Okay.
Yes.
So in that situation of the violins, how would you fix that ahead of time, like you were saying?
Well, there's a reason why. I mean, there's a template for this, like in the orchestra, right? They know, they have these ratios already figured out. They know how many violins they need per bass, per cello, So they sort that out ahead of time.
Okay.
What I'm getting at is, like, once you get there, you have what you have.
Yeah.
It's really hard to make a big difference, right? Again, assuming everything is doing. Now, are the instruments playing as loud as they can play? Can they play louder? That's a lot easier to do than hiring a whole another 8, instruments, right? Can they play louder? Can they play quieter? Right? Whatever it is, right? It's once it hits the air, it's just so much harder. And that's what line arrays do, by the way. So one of the reasons why you spend a ton of money on line arrays, so instead of a single point source loudspeaker shooting out there, why you would buy 16 loudspeakers to point at the same spot, is because line arrays, and we'll get into this later when we get into directivity, but line arrays have very specific horns in them that allow them to combine non-destructively. So they don't comb filter, which is like, right? How do they not comb filter? We'll talk about that. But it depends. But they don't comb filter. And therefore, they defy the inverse square law. So not only do they not comb filter, but they defy the inverse square law, which means when you got a line array, your sound decays only 3 dB per doubling of distance instead of 6. But it costs you a whole lot of money to defy the inverse square law. I mean, a lot, like 10 times more money you had to spend to break a law of physics. Okay? That is just not always practical. Not always practical. It's much easier to solve that problem earlier in the chain. Okay? All right, we're out of time. We will come back to this on Friday.